All right, so here it is. We're going to start talking about the heap now. So previously, up until this point in the class, we have only been talking about the stack. The remote guys, they're okay with moving forward too? Sounds like it. Okay, so we're going to start talking about the heap. And all of our overflows up until this point have happened on the stack. Local buffers are on the stack, but a whole lot of other stuff happens on the heap, especially in like object-oriented programming. So like overflows of C++ objects. And exploiting heap overflows is a lot more complicated than stack overflows. And that is because the heap is just more complicated than stack. And we're going to get into why in a second. So, hopefully you guys know the basics of what's going on here. Anyone that's on any software engineering should know this. We use a stack for local variables, so like this, that password buffer and all those kind of things. Pretty much have to know ahead of time. Not necessarily, but you pretty much have to know ahead of time what the size of your stack variables is kind of like a static storage area, even though you can push and pop. Generally the size of their static. When you need to like allocate memory on the fly, when you have no idea ahead of time of how much memory you're going to need, that's when you use the heap. So for instance, if you have some server and the size of memory needed is dependent on some user request, so like how big the file is that the user is going to upload to the server, some dynamic size of memory, that's when the heap comes into play. Whenever you don't know how big something is ahead of time, the memory has to be allocated or deallocated dynamically on the fly without knowing anything about it, that's when we're talking about the heap. Global variables also generally end up on the heap. That's why. One tricky thing about the heap is with these stack overflows, we're basically exploiting an x86 paradigm. So it's basically in the x86 architecture specification that whenever a call instruction happens, you push the return address on the stack. That's just the way x86 architectures work. Period. With the heap, there's really it's not based on the architecture. Intel didn't come along and define this is how the heap works. This is something that changes system to system and program to program. Every system provides its own heap allocator, Linux, Windows, Mac, and oftentimes individual programs provide their own heap allocator on top of that. And the way you exploit a heap allocator is completely dependent on the heap allocator implementation that is being used for the heap currently. So it can vary wildly depending on what you're exploiting. Do you guys want a break before I go into this next statement, or is everyone feeling okay? I'm going to be talking for like 45 minutes straight. So I want to know how everyone is feeling before we launch into that. And the material is pretty dry. Okay, all right. Well, let's take a 10-minute break.
Are we going to do the FD override problem tomorrow or at all? Or
probably skip it because usually it's a little bit just too involved. I mean, when I created the course, I probably created like half a day is too much material, and that's just one thing that got kind of axed because usually by that point people just cannot handle another like brutal technical lab. So, and that's right at like the finish line of where I started talking about more high-level stuff again, and usually people get out of this short thing. But all the material about how to do it, I like lay it out step by step. It's in the day 2 slides in case you're curious.
what was the GDB command? I can probably check the help, but for specifying a core file?
Just put it on the command line argument. So if you do GDB program, then space core.
Okay.
Yeah. And that's just because Linux is automatically naming the core dumps core, so you'll end up overwriting them with each other if you crash multiple applications in the same folder.
overwrite the lowest bit or the lowest byte on EVP that returns, you're going back into the main function.
Yeah.
But now you control where in the stack you reside, and since what you're passing into the command line, those 256 whatever bytes are already on the stack, you control where in that instruction pointer ends up.
Yeah. Yeah, so basically, during the vulnerable function, that allows you to take control of EVP, because it's popping that saved EVP back into EVP. And then when the main function is going to exit and doing its epilogue, it's doing move EVP, which you control, into ESP, and then pop EIP, or the return instruction. So you control ESP, so you control the contents of what's going to get popped off, and so you control EIP. But setting it up is kind of hairy. So the last thing I'm going to get through is basically talking about a basic heap allocator implementation. It's one that I wrote myself, so it sucks obviously, but it will just give you an idea, the core concepts of how heap allocators work, and then like I said before, understanding how a heap allocator works is crucial to being able to exploit heap vulnerabilities. So once you know how this basic kind of toy model works, it's easier to reason about how the bigger, more complicated Microsoft heap allocators are working. Like exploiting something like use after read vulnerability, which you see in a lot of web browser exploits, requires surgical precision understanding of the heap allocator. That way you can manipulate things. And just I'll talk about that more later if I get the opportunity to. Okay. So let's talk about the heap. Man, this is dry material. I gotta get us all psyched up for this. So goodbye stack, you're going away for now. All right, let's do this. Heap time. Rule number one, a heap club. Don't talk about heap club. Number two about heap club. Heap club grows up, not down, okay? The heap is gonna start, we're gonna be going in this direction from now on. There are markers.
Some on the other side.
Oh yeah. Okay. Can you guys see that okay? Web people, can you see that marker okay, or you want me to try to switch to a different color? Dark. I agree. We'll see how dark is. That looks not happy. Okay. The heap. Heap is growing up. Basically, the way the process address space looks in Linux, at least, is that we have a bigger scale picture. This is my process in Linux. Rock. This is my stack. Way up here, remember those addresses are like OXPF, FF, blah, 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 blah. So obviously very high in the address space. Down here, remember our code segment, all those function addresses were like 08, 04, blah, 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 blah. So this is lower end of the spectrum as well. And right above all this, we have our friend the heap. And the way that the address space works in Linux, at least, it can be different depending on the system. The heap grows up, stack grows down, and this it basically uses space a little bit more efficiently and kind of keeps them from overriding each other or doing all kinds of other nasty things. They just decided this was the most efficient way to design this process address space. And as you will see, the heap addresses are also of the form 08, 04, blah, 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 generally speaking, just because they're right above here, the text segments. Code, they're all our code in that. So, like I had mentioned, the heap is for dynamically dynamically allocating memory. Whenever you didn't know ahead of time how much memory your process was going to need, you're going to use the heap for that. And when you allocate memory on the heap, the operating system is going to basically grow and shrink the limits of your process address space. So, let's say that this is currently the limit of your process address space because you didn't need any more memory, and so the operating system didn't give you any more. That way you just didn't waste as much. So right here we'll say 08, 04, 1, 0, 0. But all of a sudden, we'll say it's the web server process. All of a sudden, you're getting attacked by Anonymous. Say you have 1,000 web users connecting to your server trying to DDoS you. And so your web server allocates a bunch more memory to handle all the process, to handle all the new user requests. And essentially what happens is your operating system is expanding the limits of your process address space to, we'll say 804.200. Then you need even more, and it grew even more up here to 804.300. And all this is the heap. You can see the heap is dynamically growing up. And each one of these limits that we hit, which is basically, like I was saying, the limit of your process address space, how much memory you have actually allocated, is called the system break. Just think of that as where, that is the point of no return. That is where my process address space ends.
So where's the stack in relation to that?
Way up here. So the heap is growing up. The stack is way up here going down. And the stack already has some pre-allocated, predefined amount of memory given to it.
For every individual process has its own stack, right?
Yes, it does.
Okay.
Yes. And every process has its own heap as well, because every process in protected mode has its own 32-bit virtual address space, isolated from the other.
So the stack is basically created not one continuous block, but two chunks, a stack block and a heap block.
But yeah, and even more than that, because there are other blocks going on that we're not talking about. But yeah, those are two of the blocks.
Okay.
So, the system break is basically just the outer limits of your addressable memory in this particular segment, and they keep in this sort of like dynamic memory segment. So each time you need more, it's going to go up and up and up. And the system break is the general terminology for kind of like the upper limit of your heap. And whenever you need more to handle more requests, that system break goes up to give you more address space and more memory to handle whatever it is you need to handle. So you can actually, I'm sure you've all seen when you program in C++ or in Linux, you use operators like new or malloc or something like that. And this is the special dynamic memory allocator, the heap allocator that you're using. But you don't have to use those. I mean, you could just adjust the system break manually and tell the operating system, okay, I need more memory, so I want to manually increase, the limits of this heap segment, because I know what I'm doing, so I'm just telling you manually expand it. That's totally legit. You can do that. And the system calls associated with that are SPRK and VRK, which is basically this, telling the operating system, okay, I need to expand the limits of my heap segment, my heap region, and the operating system will gladly do that for you. So why not just do that, use SPRK and BRK instead of using malloc and new and all that? Well, the reason is it is horribly inefficient to tell the operating system to expand your segment address space to increase the size of your segment each time you need more memory, for a number of reasons. Yeah, I won't do that on the screen, but you can just see if you were to do a debug trace on malloc, you can see that under the hood, malloc is basically using this BRK system call as well. All these memory allocators that use malloc, etc., in Windows are using something like BRK, this really powerful function call, which is just expanding the limits of your process address space. And malloc is just doing basically a bunch of fancy stuff on top of this to make it more efficient and faster. So, yeah, let's talk about why this is bad. So let's say we decided that those people that programmed malloc didn't know what they were doing, so we're just going to do it all manually ourselves. We're smarter than them. So I don't need no memory allocator. I'm just going to expand my data segment every time I need new memory. I know what I'm doing. So we do this. Let's say we got a web server, and each time a user comes in, we have to expand the segment to give ourselves more memory to handle the user. So user 1 connects, we create more memory. User 2 connects, we create more memory. User 3, more memory. User 4, more memory, etc. So this is going along fine. We all think we're very clever for having done it this way. But then all of a sudden, let's say that squiggly means used, currently in use, which means the user is still connected to the HTTP server. And say that's not used. And this is still used. So user 1 and user 4 are still connected to our web server. User 2 and 3 are not. They went, they downloaded their email or whatever, and they're done. And the problem with this is that we no longer know that these are unused, and we can't move our system break back down to give these back to the operating system. Basically, every time we expand our data segment, we have stolen memory from the system. We have stolen memory from the operating system. That is memory that King Hero claimed, our processes claimed it. And if we were just to keep expanding the data segment like this, the heap would become very fragmented, kind of like a hard drive, and we would have all these claimed all these regions of memory, stolen from the operating system that are no longer used. So basically, we would just be horribly inefficient with horribly wasteful of all this memory. We have all these unused blocks. We wouldn't know that they're there. Even if we did know they're there, we can't give them back to the operating system because this guy is still using it. If this guy wasn't using it, we could just set the system break way down here, which is tell the operating system, okay, you have all these 3 chunks of memory back, they're yours, you can take them. But since my system break is here, and I have to keep this guy, I have to keep this memory because this guy's still using the web server, I can't move the system break back down here to give this memory back to the operating system. So basically, I have just leaked these 2 chunks of memory. And you can imagine if you were to do this on a large scale of reapplication, your process would just end up sucking up huge amounts of data and you'd gridlock the system. Not to mention, it's also a very slow operation, as you can imagine, systems programming, to tell the operating system to expand your process address space in this way. And it just takes the operating system a long time to accommodate you to do that. So slow and efficient all around. Do you guys understand the basic problem here that I'm describing with just doing it with this manual brute force way of changing the limits of your process address space? So to avoid doing that, people program these fancy memory allocators, which basically keep track of those free segments I was telling you about and are able to reissue those chunks back to the program instead of stealing more memory from the operating system. And that's basically the whole purpose of these allocators like malloc, is just to reuse existing blocks and be smart about it. That way you steal as little memory from the operating system as possible. And so you can also reissue these previously claimed chunks and do it in a faster way without having to expand your process address base, because that's a slow operation. And having your memory allocator be fast is the name of the game. That's always the primary concern. Speed and efficiency. Waste as little memory as possible and allocate as fast as possible.
Does malloc necessarily call the break?
Not every time.
So if it has enough reusable stuff, it'll...
Yes, yeah. So let's assume that here's our picture again. We're still on web server land, and these two chunks of memory are unused. These ones are used because you just want it partial connected. And we get old user 5 connecting here to check his email. What if we were just expanding the, using SBRK and those things, we would have to do this, steal more memory from the operating system. What malloc does is it says, okay, you know what? I've got these two chunks of memory right here that are free, so I'm just going to give the process this one, because that's free. That way I don't have to steal this other chunk from the operating system, and I don't have to take all that time changing the limits of my process address space. So behind the scenes, that's what's happening. The heap allocator is just keeping track of what's free, what's not free, how big is it, stuff like that. That way it can quickly allocate and free stuff and just do things as quickly and efficiently as possible. Okay. Like I said, most memory allocators are front ends for BRK, SBRK, and Windows. You also get front ends for things like virtual alloc, which allocates huge blocks of memory. But they're always kind of like designer front ends for these low-level, gruesome system calls. They also do things like keeping track of the size of the chunks and grouping similar sized chunks into buckets. That way, if the user keeps requesting one size of data, he can more quickly find, there's like 500 allocation requests for 512 bytes. The heap allocator is going to be smart about keeping all those free and used chunks in one particular pool of memory. That way it can handle those more efficiently. Lots of optimizations like that. Not too important to go into, it's just, What you have to realize is that when you're talking about a heap allocator, what you're really talking about is crazy linked list programming, okay? Heap allocators are really just really complicated linked list programming. And the linked lists are just keeping track of all these heap chunks and free and used chunks of memory. And when you do a heap allocation request, it's kind of traverse those linked lists to try to find one to satisfy the user's needs. That way he doesn't have to expand the process address space and get more memory. And it'll also do things like heap defragmentation. That's an important heap defragmentation. Heap coalescing is an important part of the heap allocator. So this is our heap again. We'll say these are our individual heap chunks, heap chunks of memory. Those blocks of memory that are allocated and freed or not freed by the user. And we'll say the squiggly line means it's still in use. What the heap allocator does to increase its efficiency, or one thing that it commonly does, is whenever it sees two free blocks right next to each other, it will coalesce those blocks together to form one larger free chunk. And that's because that just defragments the heap, and you don't want a scenario where you have a lot of really small free chunks, because smaller ones are harder to use. So let's say, for instance, these are chunks of memory, Each one of them is 64 bytes. Because the user did like malloc 64 and free, char buff equals malloc 64 and free buff. That happened twice. But now the process's memory address requirements are expanding. It's handling more and more data, and it needs 100 bytes. So we just got a call for malloc 100. The heap allocator is using this crazy linked list programming and saying, okay, you know what, I've got these free chunks, but I can't give these to the user because they're only 64 bytes. So the chunk of memory has to be at least as big as the user's allocation request, and neither of these satisfy it. So if the allocator wasn't smart, it would pass those up, and it would perhaps have to take more memory from the operating system, but the best allocators, and pretty much all allocators out there these days, would say, yeah, I've got these two free ones right next to each other, so I'm just going to coalesce them into one block. That's 128 bytes. And I'm going to give that to the user, because 128 is bigger than 100. You guys all follow that? Basic requirements here. So yeah, and behind the scenes, what's happening with all this, even though it sounds pretty simple, is crazy linked list programming. So whenever you're exploiting a heap, I like to think of it as, and it's sometimes helpful to think of it as, exploiting linked lists. So we all remember from CS Programming 101 from our college days that programming linked lists was a nightmare when we were fledgling computer science students. And this is like that on Barry Bonds amounts of steroids, all right? It's crazy. So we're going to talk about my memory allocator, Corey's crappy allocator, pre-alpha version, whatever you want to call it. And understanding how that works and how its linked list works will give you a better insight into how the real production ones work. Because I didn't model it after real allocators out there. In fact, I modeled it after DL, Doug, Lee, malloc, which is what's used for Linux. But obviously a greatly simplified version. And then eventually, tomorrow probably, we'll get to exploiting that. Okay. A couple properties of Corey's crappy allocator. Mimics the general Linux implementation of malloc. So I'm not totally coming out of left field with this thing. It is kind of comparable to the real deal out there, just a simplified version of. Allocates things quickly. It's fast and allocate. It's slow on deallocate. We'll see why. Does not try to coalesce anything. That's basically because I was way too lazy to program the linked list black magic voodoo involved with coalescing the free chunks. I do keep track of free chunks, so previously claimed chunks that have now been freed. That way I can reissue those to the user instead of stealing more memory from the operating system with that system break system call. Okay, so let's talk about how this thing is implemented. The core concepts here. At all times, I maintain a doubly linked list, forwards and backwards pointers of all the free chunks that I have allocated with system break and that are now no longer used by the user. So anything that was alloced and then de-alloced, that is on a linked list. And then what happens is whenever another allocation request comes in, I traverse that linked list looking for any free chunks I have that are bigger than the user's allocation request so that I can give them to the user without having to use system break again.
So I have a
go for it.
question. What defines memory as being free? Does that mean it's not allocated or is it like in use? How does...
It's free because the programmer has told you it's free. It's free because the programmer has told you free this memory chunk. So when you're doing C programming, you do like malloc and then free, and if you don't do free, it's a memory leak. So if the programmer doesn't tell you that it's not free, it ain't your fault. It's the programmer's fault. It's a memory leak. We ain't talking about, Fairyland Python where the interpreter does everything for you. This is the real deal. If you make a mistake, too bad.
Yeah.
So yeah, this is not a type-safe language like Python or Ruby or something like that. If you allocate something and you don't free it, then That's the programmer's fault, you know, that ain't my fault at all. It's not full of nice, happy things that will come and fix our problems like Java or Python that keep track of all this for us. And this is why C is faster, because, you know, the programmer is responsible for doing all this on their own. They don't rely on something like Python or Ruby to keep track of this themselves. So that was a little tangent on that. Meta information about the pre-chunks. Okay. Let me draw a picture of this as well. Lots of pictures of heaps, lots of pictures. Okay, so I'm defining a chunk of memory as any block of memory that the user has allocked, okay? So when I do like malloc 100, that creates a 100 byte chunk of memory. And what these chunks of memory look like is, I'm going to keep going upwards. We have this, and let's say the user mem sets a, 100. What our chunk looks like then is all of this is the user data, okay? This is the user data portion of the chunk. So right now it's full of A. What's down here is the chunk meta information. And this is how it works with the real implementations as well. In the beginning of all these chunks, it stores things like, is this chunk currently free? So 3 equals 0, size equals 100. And another thing it stores am I writing too low? Can you guys see that? Remember how I said that there's a doubly linked list of all the pre-chunks, right? That list is actually stored at the beginning of these chunks as well. Okay, so the information for that linked list is stored at the beginning of all these chunks on the heap. So we have this chunk meta information, which contains basically a Boolean value. Is it free or is it not free? The size, in this case, 100 bytes. And the next and the previous pointer, which point off to the previous free chunk and the next free chunk. And basically, the allocator is going to use those chunks to help traverse the heap more quickly when looking for free chunks when an allocation request comes in. All right? So it's just important to realize that at the beginning of this memory, with the malloc, there's actually this chunk meta information. So buff actually points to right here. And at buff minus 10, points right here. So obviously I'm not returning a pointer to the chunk meta information, or else when you would use that data, you would overwrite your own chunk meta information and calamity would ensue. So the allocator is smart enough to increase the pointer a little bit to so that the pointer returned to the process is pointing into this user writable region of the chunk. You guys got that? I know this part's a little bit crazy. And more. I know this is more and more.
But you could theoretically just take the pointer, subtract 10, start.
You could. And in fact, if you do an allocation, right now, if you were to open up GCC and do char buff equals malloc 100, and then go into a debugger and look at the address associated with buff minus OX10, you would see meta information similar to this. This is how most of the memory allocators do it.
Is that writable?
Yeah, it is. So you can overflow these regions, right? If you just write your program to change these by default, that's not really a vulnerability because you're just on purpose, changing your own chunk meta information. It's like, yeah, okay, whatever. But these heap chunks are contiguous to each other. So you can imagine I have another chunk starting up here. So if I had an overflow in this chunk, it would overwrite this, and it would overwrite this next chunk's meta information. Okay, so an important note there is you're not writing, you're overflowing your own chunk meta information. Since we're growing up, we'll be overflowing the next chunk's meta information, right? And by overflowing these values, you can basically cause arbitrary code execution, which we'll see later on. And, you know, let's keep going with the implementation description. So alloc, so we always have that doubly linked list of pre-chunks. Meta information at the beginning of the chunks, like I just showed you. Every time alloc is called, we walk that linked list, which is, you know, the pointers of which are stored in the beginning of those chunks, looking for a chunk that satisfies a request. So let's say the allocation request was for 100. There's a head of the list, and it would start there, and it would start traversing these pointers, and it would say, is it free? Okay, if it's free, is the size greater than the size requested? If the process requested OX 80 bytes, we requested OX 100 bytes, we can't give it a chunk of only OX 80 bytes. You know, it has to satisfy the memory requirements, or else, you know, you're gonna cause a buffer overflow just because your implementation sucks, not because of programming mistake. So yeah, traversing a linked list, is it free? Is the size big enough? If not, keep going. If it is, you know, give it to the user.
Even if it's much larger than what they're requesting?
Yes, yeah, very insightful stuff. Smart allocators like malloc, obviously, if you requested 100 bytes, and you came across a chunk that was 4,000 bytes, the allocator would say, you know what, I'm saving this one for someone more important, so we'll keep on moving. My allocator does not, okay? If you request 1 byte and it comes across a 1,000,000 byte chunk, it's going to say, yes, we satisfy the requirements on give you to the process. So, yeah, that's, you know, obviously if you're running a real memory allocator used in a production environment, you would want to be smart about stuff like that. I feel bad for Bill, so we'll keep walking back and forth to the board. And then the dealloc function basically just sets that one bit field in the meta information to not free anymore. Free equals 0. Okay, so this is pretty much just like what I showed you before. This is one of our chunks that we get with like an alloc. That's what my allocator uses, alloc and dealloc, not malloc and free, alloc and deallocs. This is the chunk meta information, the actual C struct. Available, size, the other side is just a 32-bit integer instead of like a Boolean one value, doesn't matter. Pointers to the next free chunk and the previous free chunk. So we're storing the linked list in the beginning of the chunk information. One question I often get asked is, why do they store the chunk, the linked list pointers in the beginning of the chunk? It's a little bit strange. You could just store this out of band kind of in your own linked list that's not stored in the chunk meta information. And the reason is just for size and space efficiency, because memory allocators are usually pretty smart about putting this stuff in the regions of data that are currently not being used. So it just comes down to space efficiency. So memory allocators are all about being space efficient. Obviously, if your whole goal in life is to allocate memory and be as efficient as possible with the operating system, you're also going to employ clever programming tricks like this, just to waste less memory from the operating system with just the handling the meta information by your heap allocator. So yeah, that's what the chunk looks like. Everyone has a general understanding of what these memory chunks are, and what's for the beginning, and why I have this information here. You guys all got that? Remote guys, do you follow this okay? Okay, good. Okay, so the alloc algorithm, the allocation algorithm, like I said before, we traverse that linked list. If one is found to be free and a suitable size, we basically take it off the linked list. We don't want to serve up the same chunk to the process twice. That would cause lots of bad problems. So once we give it back to the process, we have to make sure that we don't give it up again until the programmer has marked it free. Okay. Yeah.
I'm a little confused about, it's a linked list of free chunks.
Yeah.
So that implies that they are free, or because you have a premium value to tell them.
Yeah, sorry. Yeah, good point. So for the allocation request, that's why it's a fast alloc. I don't have to walk over all the chunks, only the free ones, right? So forget that I said check if it's free or not. It automatically knows that it's free, okay? Because you're right, it's on the free list, so it is free. The only thing it's checking is the size suitable. Is the chunk big enough to satisfy the request? In the last resort, if we have found no chunk that is big enough to satisfy the process's memory needs, then we're just going to bite the bullet and tell the operating system, all right, look, dog, I'm sorry, but I got to get more memory from you. So give me another megabyte. And I know that's hurting, but I got to do it. And that's the way it works. Okay, so I'll get some boring stuff here. This is just the implementation of the heap allocator, the alloc function. Hopefully you guys have all worked with C code a little bit before, but hopefully it's self-explanatory even without that. It's basically just doing what I just described to you with the exception of this little alloc initialization thing, which means if it's the first alloc call ever, let's just set up some meta information like where does my heap start? The start and end are the same at this point because I haven't expanded the heap at all. And then right here, I'm just traversing that linked list of free chunks and then checking the size. Is it big enough? And if it's big enough, mark it as no longer available. Set it up to be returned to the user, and then unlink it from the linked list. If we're giving it to the user, it can no longer be on the linked list of free chunks, right? We all got that? So really not too bad. Unlinked chunk, this should just look like linked list stuff that you probably tried to forget. It's just removing the chunk we just claimed off of the linked list by setting the previous and next pointers equal to each other. I'll talk more about that later when we get to the exploitation scenario. You just have to know the general gist of what this is doing is just taking it off that linked list. Unlink it from the list. Okay. Dalloc, I kind of got lazy when I was programming this because I want to avoid as much complicated linked list programming as possible. Whenever you have a dalloc, we mark the chunk as available. That's free. We just set that 1-bit value to 1. And then I reconstruct the whole linked list. I throw everything away that I used to know and reconstruct it all from scratch. That's because that was easier than having to program the linked list code associated with this. So I basically walk over the whole linked list, over the whole heap, keeping track of what chunks I've seen and whether or not they're free. And then based on what I've seen, I construct my linked list. So just remember, when dalloc happens, everything is basically reconstructed from scratch. Because that was easier before your program did crazy linked list stuff.
So what this does is it takes, if someone were to return the memory, it's adding it back to your linked list?
Yes, it is.
Okay. Is there a reason why, because you said you reconstructed, what about just tacking it on the end? Is there some...
There's a lot of implementation details there that make the implementation really gruesome. Basically. All you have to know is that dalloc reconstructs everything, but at the end of the day, once dalloc is done, you still have that linked list of free chunks. That is like the invariant in the heap allocator. You always have the linked list, a double linked list of free chunks currently in the heap.
Is that typical that the list of free chunks will be in contiguous order that they are in memory? Like you were suggesting it, otherwise if you tack things onto the end, they would be, your list would be jumping around.
It really depends. I know what you're saying, and they try to do pretty complicated things to keep things like in proximity together just to make the traversal faster, more efficient, but it really depends on the implementation. They do all kinds of crazy things to try to make these just a fraction faster, which is why they're so complicated. This is basically what it's called to just reconstruct the linked list. Basically, I delete everything I know, and I traverse over the whole heap, not just the free chunks, to keep track of what's free, what's not free, and then rebuild the linked list based on that information. Okay. So, if you fire up your VM, you will find in the alloc directory /home/pin/alloc, my code for this stuff. And this just shows typical use of the heap allocator. You know, I'm allocating something, I'm deallocating and allocating and deallocating. And I even threw in this handy meta function, dump heap, which just dumps all the chunk meta information whenever you call that, just for to help us debug the heap and what's going on with it. So, use GCC to compile this, by the way. We're done with TCC for a while, so GCC. GCC-O, alloc user. Like so, they compile it. Alloc user is the file I just showed you, the one that's just doing the simple allocations and deallocations. And alloc.c contains the actual implementation of the heap allocator that I programmed. And what you see here in this ugly colored text is I actually spent a long time figuring out how to change the color of the output because I thought that you guys would like it. And unanimously, people hated that. It really hurts my feelings. So we can change that later on. For now, you can just see I'm printing out some information. These are all just prints that happen courtesy of the allocator. I programmed these printf statements into the allocation implementation just so you can have a better idea of what's going on when you perform the allocs and deallocs. So you can see heap end and heap start are now 0804800. I allocated some memory, returning it to the user. The bright awful green is like the current chunks basically on the heap, and we can see the memory address associated with the chunk, the size of the chunk, whether or not it's available, and then next free and previous free pointers. There are none. This is the only chunk on there. And then available equals 1 because dealloc was called on that chunk. Still null values for these pointers because this is the only free chunk on the list. Then we can see that another allocation request comes in, and it's just serving up that previously allocated chunk. So nothing too fancy. You guys can play around with some if you want by just editing that alloc user file, you know, performing allocations and deallocations. Like so. So yeah, that's basically the heap allocator in action. And what's going to happen is we're going to end up exploiting an overflow in the heap allocator. We're seeing how heap overflow is. We'll have an overflow that's similar to what you saw in the stack overflow exercises, except it's going to be a lot different because we're not overwriting a return address. We're going to overwrite that chunk meta information and use that to cause arbitrary code execution. So, yeah, I'm just trying to justify again that what I'm showing you guys isn't very contrived. I didn't just make this up for no reason. This actually does model a lot of heap allocators out there. As you can see, I took this off like the DL Malloc website, and it's describing as well the chunk meta information that it uses. So it also has things like size, free, and all kinds of stuff like that. Very similar to what I'm doing. If you want to become an exploit aficionado, I would suggest that you read articles like this because, like I said before, knowing the gruesome details of how memory allocators works is critical to being able to exploit heap overflows. And these days, a lot of overflows happen on the heap, not on the stack, because people are programmers are more aware of overflows happening on the stack, and stack overflows are maybe a little bit easier to find than heap overflows. And heap overflows are growing in number a little bit more just because they're a little bit harder to find because generally you're talking about global variables that are accessed in very complicated ways. So it's they can just hide themselves a little bit better than if you see like string copy to a local buffer. How do people feel about the understanding of the implementation of the heap allocator? Do you guys have a basic idea of what's going on there? Yeah. Okay. All right. So yeah, I know that was really boring, guys. Thanks for sitting through it. But like I said before, you just have to understand the implementation of what's going on with heap allocator before you can expect to be able to hack it. Yeah, heap overflows are generally always harder to exploit than stack overflows. You'll get more street cred if you exploit cool heap overflows and stack overflows. That's the way it is. As you can see, this was just taken off like an exploit website. There's a lot of heap overflows out there today. These things are all over the place. And even exploiting other types of capabilities like use after free that don't necessarily involve overflows require great understanding of heap allocator. So it's worth your while to know this stuff, even though it's very boring. Okay, I think you guys are pretty tired, so it's probably a decent stopping place for today. When we come in tomorrow, we will start talking about how we actually exploit these heap allocators, and we'll go through an example where we exploit something like basic bulbs and get our shell code to execute by exploiting a heap overflow. So yeah, we'll try to meet back up here tomorrow at 8:30. If that sounds okay to you guys. And if you have any questions, please feel free to stick around and I'll try to explain more stuff about this to you. So yeah, there you go. Day one. You survived. For those of you that are still sticking around here, I assume that your curiosity hasn't been satisfied. So I'll just give you a taste of what the next lab will be so you can think about it. Those of you that want to leave, feel free to take off. I know that you guys got to get going. But so this looks very similar to basic bowling, right? When I try to overflow that buffer, oh man. So right, when I overflow the buffer, you know, just like print 150 A's, notice I don't get a crash. So normally, like if this was a stack overflow, we get EIP equals 41414141 in the crash. So for those of you that want something to think about tomorrow, or tonight rather, think about, we're trying to get alloc user to crash with an overflow-like scenario like this. So I want you to overflow a chunk, and then some alloc or dealloc later get a crash. Because one important rule that I'll say for this class that it's probably the most important thing you should take home is that if you can hack it, you can crash it. So if there's an exploitable scenario, you can definitely cause a process to crash, right? Because if you can change DIP, you can obviously change DIP to something bogus, which is going to cause a crash. So I want you to try to crash the allocator implementation, not with bad programming, with like double frame something or double allocating something. That doesn't count. That's just like a programming mistake. But try to get it to crash based on some type of overflow scenario. So overflow buff one, then maybe, or maybe have two chunks and overflow one into the other one and try to do an allocation, some type of operation on the other chunk, and maybe that'll cause a crash. So basically what you're going to try to do is position the heap such that an overflow in one corrupts some meta information in the other one, and then allocation or deallocation on that corrupted chunk meta information is going to cause a crash. So think about that, try to do that, and we'll talk about, what's going on and how to exploit that tomorrow.